Welcome to the third video in the coupled oscillator series. Again, this time we're going to study this particular system of two cards attached to each other with a spring and also individually attached to a wall by two other springs. It's our prototypical example of two coupled oscillators. This time we're going to study the particular case of this middle spring being much weaker than the others. So we have basically K prime much less than K. Otherwise, it's exactly the same case as what we studied in the last video. And then we can jump immediately into saying what the K and M matrices are. The M matrix is the same as before. It is just simply equal to M0, 0, M, while the K matrix is a little more complicated, but not much. It becomes K plus K prime and minus K prime, and then just the same thing but in the opposite order on the second line. So this means then that the matrix that we want to take the determinant of, which is K minus omega squared M, is just equal to the following. And then we just have to take the determinant of this. This is particularly easy in this case because if you take the determinant of a matrix that has the following form, A, B, B, A, you know that's just equal to A squared minus B squared equals A plus B times A minus B. So you can basically just read off what the result is going to be. We know that then that the determinant of K minus omega squared M is therefore equal to K minus M omega squared times K plus 2K prime minus M omega squared. And this has to equal to 0 when omega is the eigenfrequency of the system. Okay, so what we find then are two modes, because this is a second order polynomial with two solutions for omega. So we have two modes. So the first one I'm going to call mode A, has omega A equals the square root of K over M. And then the second one is mode B, and it has omega B, its eigenfrequency, is the square root of K plus 2K prime over M. Now the next step then is to calculate the normal modes, and we do that just by writing out this in the two cases. So we have for mode A, we have that so the matrix is just equal to K prime minus K prime on the first row, and then minus K prime and K prime on the second row. This is proportional to the matrix 1, minus 1, minus 1, 1. Okay. And then we can do the same thing for mode B. Indicate those with circles, I guess. K minus omega squared M double bar equals, and all that I'm doing here is I'm just inserting this where omega is. Well, I'm already removing the M here from the outset. like so. So it's just minus k prime minus k prime minus k prime minus k prime. And this is proportional then to minus 1, minus 1, minus 1, and minus 1. These are actually exactly the same result that we got when we had k prime equal to k. So we have the same modes. If you remember, this one led us to the case that the two amplitudes for the two cards are equal. So the amplitude of k card 1, A1 equals A2. That's the case here. So A1 equals A2. And for mode 2, we have the opposite, that A1 equals minus A2. We can call this the in-sync mode, and this is the out-of-sync mode, or the symmetric and anti-symmetric mode, whichever you like. Different terminologies prevail. All right. So if we have that, that tells us, how they move. But it is profitable now to write these frequencies, the eigenfrequencies, on a slightly different form, or use a slightly different combination of them in order to see what would happen in a typical case. So let's erase this. And what I'm going to do now is I'm going to introduce two other frequencies. I'm going to say that, well, omega A is actually equal to omega 0 plus actually minus epsilon. And I'm going to say that omega B equals omega 0 plus epsilon. So the new things I'm introducing here are omega naught and epsilon. Omega naught is, if you just look at this equation and solve for omega naught, you can see that that is just omega A plus omega B over 2, just the average value of the two frequencies, the two eigenfrequencies. And epsilon, it's just half their difference. And if we're in the limit now where k prime is much less than k, well, the difference between omega A and omega B is small, right? They only differ by this factor of 2, k prime here inside the square root. So we have then, because k prime is much less than k, that epsilon is much less than omega naught. And that will turn out to be important shortly. Okay. So if you now want to write down what the total motion, the possible total motion of the system looks like, well, you do that first using the complex representation. So we have that z of t equals some initial amplitude, and now we are dealing with mode 1, so everything is in phase. So we have 1, 1 there for the amplitudes, times e to the I, and then we will multiply by omega A, but omega A we decided we're going to write as omega naught minus epsilon times t. And then we have the same thing for the other mode, which is now out of phase. And that becomes then e to the I omega naught plus epsilon times t. And we can rewrite this, if we like, as c times 1, 1 times e to the minus I epsilon t plus c2 1 minus 1 e to the I epsilon t, and then times e to the I omega naught t. There. So this is now the full solution to this problem. To get a little bit more insight into what is actually going on here, I'm going to look specifically at the case where C1 equals C2. I mean, C2 and 1 and C2 are the amplitudes of, or the relative amplitudes of the two modes, and you can pick them any way you like. So we're now going to study the specific case of C1 equals C2. So I'm going to say that C1 equals C2 equals A over 2. So if that's the case, then we know that Z of t equals A over 2 times e to the minus I epsilon t plus e to the I epsilon t for the first component, and the second component is e to the I minus I epsilon t minus e to the I epsilon t multiplies e to the I omega naught t. And we can see now, because of the definition of cosines and sines, we can see this just becomes equals to a times cosine of epsilon t sine of epsilon t times e to the I omega naught t. The actual motion of the cart is the real portion of z, so that's going to be equal to going to be equal to that. So the first mode, or the first cart 1, is moving as a cosine epsilon t times cosine omega naught t, and the second one is moving as a sine epsilon t sine omega naught t. So for comparison, let's bring this up here so that we can see it simultaneously with the figure. So that's the solution that describes how these guys move. Now the question is, what does this actually look like? And if you plot them, you get something like this. Well, let me just erase a little bit more things here. Okay, so this is the solution to the problem. This is what the solutions look like plotted. So what we can see is happening here is that when we start out, all the motion is only in the first cart, and then it gradually gets transferred into motion in the second cart, and then it gets transferred back again. And this type of pattern, this type of behavior, is known as beating. Mathematically, it's the same phenomenon as an interference pattern. Essentially, this occurs because the two different frequencies, this frequency here, omega A and omega B, beat against each other, and then you get this characteristic pattern where the time scale for transferring motion from one cart to the other, that will be t sub tr for transfer, t transfer is equal to pi over 2 epsilon. So to remind you, epsilon is just half the frequency difference between omega b and omega a. So the transfer time therefore is equal to pi divided by omega b minus omega a. So the closer they are to each other, the more slowly the motion gets transferred from one cart to the other, and that hangs together with k prime, the coupling constant, being smaller. So if you will, we can plot, if this is k prime here, then k prime, if this is k prime, then we can plot the two eigenfrequencies as a function of k prime, and then it looks roughly like this, that if k prime is 0, That is, there is no spring here at all, and there's no difference between the frequency of card 1 and card 2. They both oscillate at exactly the same frequency, and we have a degenerate system. The two eigenfrequencies are the same. If we introduce a non-zero k prime, we move away from degeneracy. You say the degeneracy is lifted. We have two different eigenfrequencies, one which corresponds to in-sync motion of the two cards back and forth, and the other one which is the out-of-sync motion. And the difference between the two frequencies specify the time scale, like this, for which the motion, or the energy really, is transferred from one card to the other. So this is what's happening here. The energy from card 1 at this time here, that's when all the kinetic and all the potential energy is contained in this card and the spring, and then that it's transferred then to card 2 over a time scale that equals pi divided by omega b minus omega a. And this is a very important phenomenon, especially in quantum mechanics. Chemical bonding can be described with essentially the same kind of mathematical formalism as kind of phenomena such as optical excitation of electrons in semiconductors and in optically active molecules. So we have now solved a couple of different cases of coupled oscillators, relatively simple ones. Basically, we have done so starting from Newton's second law. And as you might guess, there is a way to do this using a Lagrangian approach too, which comes in handy in more complicated cases. And that will be the subject of the next video.